Welcome to SilverTechGuide, where we explore cutting-edge health technologies reshaping human longevity. Today, we dive into the fascinating world of digital cognitive twins, AI-powered simulations modeling the aging brain. Imagine a virtual mirror of your brain, a digital twin that learns your neural patterns, predicts vulnerabilities, and helps safeguard cognitive function before decline occurs. Think of this AI as a lighthouse guiding you through a health storm. Every synapse, every neuron is mapped, offering insights no traditional scan can provide. Digital cognitive twins replicate your unique neural architecture, including dendritic pathways, synaptic strengths, and neurotransmitter activity. This isn't generic AI, it's personalized simulation. Researchers feed the system massive datasets from MRIs, PET scans, and cognitive assessments, training it to forecast subtle changes years before symptoms appear. Think of it like weather forecasting, but for the brain. By analyzing patterns over time, AI predicts storms of cognitive decline with impressive accuracy. These digital twins mirror the real brain's physiology, integrating blood flow, neuron firing rates, and even sleep-dependent memory consolidation patterns. Clinicians can visualize areas of early atrophy, changes in hippocampal volume, or irregular cortical thinning, enabling preemptive interventions. The AI continuously updates, incorporating new cognitive tests and lifestyle metrics, hydration, sleep, activity, creating a living learning model of your brain. Virtual reality exercises can then be prescribed, tailored by the twins' predictions, targeting memory circuits or attention pathways most at risk. What makes digital cognitive twins revolutionary is their dynamic adaptability. As your brain changes, the twin adapts, recalibrates predictions, and guides interventions in real time. Think of each input, blood biomarkers, activity tracking, cognitive testing, as puzzle pieces that the AI assembles to reveal the complete brain health picture. Traditional imaging shows snapshots. Digital twins create a time-lapse movie of your brain's functional trajectory, forecasting risk decades in advance. Each synapse in the model is simulated using probabilistic algorithms, reflecting the real-world stochasticity of neural firing, capturing the brain's complexity. Clinicians can design bespoke cognitive regimens, adjusting difficulty, duration, and modality according to twin-predicted decline curves. Even sleep cycles are incorporated. REM and slow-wave sleep patterns affect memory consolidation, and the twin can detect subtle deviations impacting cognition. This allows population-level insights. Trends in neurodegenerative risk can be detected earlier than ever without invasive procedures. By simulating various scenarios, the AI can suggest lifestyle or medical interventions to slow predicted atrophy in memory-critical regions. These interventions aren't generic. They're personalized, guided by precise AI models reflecting your real-time neural integrity. Think of vulnerable hippocampal circuits as canaries in a coal mine. The twin spots early warning signs before functional decline emerges. The system's predictive power improves continuously, learning from every new scan, test, or activity metric, refining forecasts over months and years. Cognitive training games prescribed by the twin target precise circuits, attention, executive function, or visuospatial reasoning, maximizing neuroplastic benefit. Neuroplasticity isn't theoretical here. The twin can show the growth of new dendritic spines reflecting your brain's response to exercises. Imagine walking through a virtual garden where every memory challenge strengthens real neural networks predicted by your twin. Subtle cortical thinning can be tracked precisely, allowing interventions targeting regions critical for language, memory, or executive control. Group-level simulations also optimize social engagement activities, proven to maintain hippocampal volume and reduce stress hormone impact. The twin isn't static. It self-adjusts as new neurobiological insights emerge, integrating cutting-edge research from neuroimaging and genomics. Some neurons are pruned, others strengthened. The twin models this dynamic, offering insight into which circuits need stimulation. Attention and working memory exercises can be fine-tuned, guided by twin-predicted attentional network vulnerabilities. Dopamine, serotonin, acetylcholine, all modeled in real time, showing how chemical fluctuations affect cognition and mood. This allows clinicians to create intervention protocols that aren't guesswork. They're precise, proactive, and predictive. Side-by-side simulations illustrate potential decline and the effects of intervention, helping patients understand their brain's trajectory. VR environments allow safe, controlled stimulation of at-risk circuits, guided by twin predictions, strengthening memory retention. Progress is tracked continuously, reinforcing motivation and adjusting therapy intensity according to real-time neural responses. Connectivity maps demonstrate network integrity, highlighting areas where interventions are working or need reinforcement. Reaction time, processing speed, and decision-making metrics feed back into the twin, enhancing its predictive precision. Simulations allow what-if analyses. What happens if activity declines, sleep worsens, or stress increases, and interventions to counteract them. Clinicians can prioritize high-risk areas first, maximizing intervention efficacy while reducing unnecessary cognitive strain. Problem-solving, memory, and attention exercises are curated specifically for your predicted neural vulnerabilities, ensuring targeted neuroplasticity. Every action feeds the AI's probabilistic models, refining risk prediction with unprecedented accuracy for each individual. Heat maps reveal active versus dormant circuits, allowing clinicians to focus stimulation where it matters most. Mindfulness and meditation exercises can be integrated, optimizing neurochemical balance and reducing stress-induced synaptic weakening. Simulated responses help personalize nutrition, activity, and cognitive tasks, ensuring interventions reinforce real neural growth. Socially immersive cognitive training enhances memory and executive function while stimulating hippocampal networks predicted as vulnerable. Every graph tells a story: risk zones, progress markers, intervention impact, helping clinicians adjust therapy with surgical precision. Personalized VR scenarios evolve dynamically as the twin learns which circuits respond best, maximizing efficacy while reducing cognitive fatigue. Complex task simulations improve executive function and decision-making, reinforcing neural circuits vulnerable to age-related decline. Longitudinal tracking allows detection of subtle thinning, letting clinicians preempt decline and enhance targeted neuroplasticity exercises. Predictive interventions include cognitive training, lifestyle adjustments, and personalized therapies, all derived from twin modeling. Neural regeneration simulations show how targeted exercises may strengthen or restore connectivity in vulnerable networks. Real-time feedback ensures exercises remain challenging yet achievable, reinforcing engagement and maximizing neuroplastic gains. Algorithms constantly refine themselves, integrating new data to provide ever-improving predictions and intervention recommendations. Cerebral blood flow and metabolic activity are simulated, highlighting regions at risk of hypoperfusion or energy deficits. Memory recall exercises are targeted to predicted weak circuits, reinforcing neuronal firing patterns for lasting cognitive benefits. Predictive scenarios allow patients to see how exercise, diet, and sleep could influence neural trajectories decades ahead. Data-driven adjustments personalize interventions, optimizing intensity, duration, and complexity for maximum cognitive resilience. Twin-guided stimulation shows how targeted cognitive and lifestyle interventions can reverse predicted synaptic weakening. Exercises challenge memory and executive function simultaneously, aligning with AI-predicted vulnerable networks for optimal reinforcement. The twin identifies high-risk circuits for timely interventions, maximizing cognitive preservation and extending brain health span. Mapping dopamine and acetylcholine fluctuations guides interventions to enhance attention, memory, and mood regulation. The VR environment adapts in real time, offering challenges precisely calibrated to the twins' predictions, strengthening targeted circuits. Continuous monitoring ensures interventions remain aligned with changing neural patterns, maintaining optimal engagement and stimulation. Reaction time and attentional accuracy feedback into the twin, refining predictions and intervention specificity for maximum effect. Twin simulations show projected neurodegeneration pathways, helping clinicians design interventions to halt or reverse predicted decline. Cognitive exercises are tailored to predicted vulnerabilities, maximizing neuroplastic growth and preserving executive function. Targeted interventions guided by the twin demonstrate measurable strengthening of synaptic connections over weeks and months. Engagement metrics inform adjustments, ensuring therapies remain challenging, personalized, and maximally effective. Group therapy leverages social interaction, further enhancing neural resilience and emotional well-being. Twin modeling visualizes real-time connectivity changes, showing progress or areas needing additional stimulation. Predictions inform both patients and clinicians, enabling proactive, precise, and personalized cognitive care strategies. Adaptive exercises challenge memory and executive function just enough to stimulate optimal neuroplastic growth. Neurochemical feedback loops allow clinicians to fine-tune interventions for maximum neurotransmitter balance and cognitive support. Mindfulness sessions, guided by twin predictions, enhance cortical thickness and reduce stress-related synaptic weakening. Twin models allow continuous comparison of predicted and observed progress, ensuring interventions remain on track. Reinforcing previously weakened circuits ensures lasting neuroplastic gains and preserves cognitive independence. Longitudinal data allows clinicians to fine-tune personalized plans for sustained brain health over years. Visualization of active networks helps prioritize interventions for attention, memory, and executive function circuits most at risk. Immersive programs engage multiple modalities simultaneously, maximizing neuroplastic adaptation and cognitive resilience. The twin predicts memory retention trajectories, highlighting which circuits remain resilient and which may require intervention. This allows clinicians to act before noticeable decline occurs. Immersive VR exercises challenge spatial reasoning, memory recall, and attention networks simultaneously, tailored exactly to your brain's predicted vulnerabilities. By comparing your twin with population-level aging models, the AI identifies deviations that indicate early cognitive stress or neural inefficiency. Every task completed strengthens the relevant synaptic connections, reflecting real-world neuroplastic changes predicted by your digital twin. Researchers refine parameters daily, incorporating the latest scan data and behavioral metrics to improve accuracy of predictions and suggested interventions. Dual task exercises enhance executive function, attention, and working memory circuits simultaneously, aligning with the twins' predicted risk regions. The twins' heat maps visualize areas of increased connectivity, showing exactly where interventions are having measurable impact on circuit resilience. This integration of AI, VR, and personalized neuroplastic exercises exemplifies how digital cognitive twins transform proactive brain healthcare, preserving independence and enhancing quality of life. That concludes our deep dive into digital cognitive twins, AI systems transforming brain health. From predictive simulations to tailored cognitive interventions, these technologies empower proactive neural care. Every synapse, every connection, every neural pathway can now be monitored and optimized with precision. Digital twins don't just model the brain, they guide actionable steps to preserve memory, attention, and executive function. Thank you for watching SilverTechGuide, where science meets innovation to enhance human potential.